Okay, so we now have done weight, normal force, friction. So the last one that we care about is tension. Tension. T. Now this is going to be exciting. You're going to be happy about this. You ready? It's a scalar. A scalar, we're back to high school physics, algebra-based, yay! A scalar property of a string or rope or cable. I'm just going to call everything a rope, right? But you'll see problems, string, rope, cable, whatever you want. And it's in newtons. How can a scalar be in newtons? Well, a unit doesn't have a direction. A quantity has a direction. So a scalar can be in newtons. Right? Now, here's the sad part. But we're going to talk about the tension force. And the distinction is actually important. The tension force, which is also T, but with a vector sign on it, okay, is the force a string or rope applies. The force a rope applies to an object. Right, to an object at the point of attachment. At the point of attachment. All right, yes. What is the magnitude of the tension force? It's equal to the tension. So the rope is under a tension of 10 newtons. Then if that rope is attached to something, it'll pull it at 10 newtons. Right? So T, it is both the scalar property of the string and it also, without the vector stuff on it, is also the magnitude of the force. It's both. Okay? So you can just think of it as a force. It's fine. Just wanted to get a little specific. Technically, you got to realize it's really a property, scalar property. Let's see. The direction of this force is along the string, or the rope. Whatever direction the rope is pulling at, that's the direction of the force. So you just draw a little force along the rope, and you put a T with a vector sign on it, and you're off to the races. Okay? So let's do the simplest possible case of a tension problem. Well, not the simplest, I guess. Okay, you know what that means? That's ice. Okay? This is a hard wooden frictiony surface. This is an ice surface. So mu static equals 0, and mu kinetic equals 0. So that's my way of saying a frictionless surface. So we've got a box on a frictionless surface like this, and we have a rope attached to it, and the rope is like that. And for the rope, the tension equals, did I do numbers? 20 newtons. Right? All right. A rope with a scalar tension of 20 newtons is pulling at 30 degrees. What is that going to do? I don't have a mass in here. We're just doing forces. Well, all you do is you say, well, the force is along the rope. There's the tension vector right there. It's along the rope, and it's whatever length is 20 newtons. In your cartoon, it doesn't matter. We don't draw all the vectors perfectly to scale. So if you want to do a free body diagram, unless you're doing this in deep space, you would probably have mg down. And would you still have a normal force? Does ice create a normal force? It's frictionless. Yes, it does. Right. So friction and normal, nothing to do with each other. It'll still create a normal force like that. And then the tension is going to come along and just apply this vector at 30 degrees, or whatever I said it was. Like that. So there's your free body diagram. 3 forces, normal, mg, and tension. If it's not moving, do I need to draw a friction force on it? No. Right? If it's not moving, oh no, I would need a friction. Well, this is going to move. Never mind. Is this going to move? Yes. No friction because it's on ice. There's no friction. But if you look at it just visually, you can tell there's nothing canceling the right horizontal tension force. So it's going to pull, right? So it looks like this. Imagine this is a frictionless surface. Look at that demonstration. That's changing your life right there. Yeah. Okay. Now let's calculate how this tension force we're applying is going to change things. Okay. So let's do the F and the Y and the force and the X, and just apply Newton's second law and see if everything's the same or something different, new, is exciting is happening here. So sum of the forces in the Y equals the mass times the acceleration in the Y. Okay. Of course, it's not moving in the Y because we know we're not going to lift it, or we might. But let's say it only moves in one dimension. Then we would say, okay, let's add up all the forces in the y. The normal force is up, right? Minus mg is down. And tension, the vertical component of tension, here's my right triangle, the vertical component is sine. Because it's standard, we defined angles the right way. It's t sine theta, and it's up. Sine of 30 degrees in this case. And I'm going to say the problem told you that it's sliding along the ground. It's not being lifted in the air. So we'll say the acceleration up is 0. Okay. So you can already see this has already done something a little bit different, is the normal force is reduced. Right? N is usually just mg, but now it's mg minus t sine of 30 degrees. Right? So normal is reduced. Because you're pulling up on it a little bit. You could also not do it at an angle. I could also reduce the normal force between the table and the block just by pulling like this. And if I pull hard enough, it goes up in the air. But if you pull at an angle, it's the same thing. When I do this, I'm reducing the normal force. If I'm reducing the normal force, what am I also reducing? The friction. Yeah, the static friction is less if I pull up at a high angle. It's more if I pull at a low angle. So actually, it is important. Even the y, which looks pointless, something important happens. You change the normal force. What about the x? Sum of the forces in the x equals mass times acceleration in the x. So in the x, we have t cosine theta going forward. And what do we have pulling it back? Nothing, right? Because it's frictionless. I should have put some friction in this, I guess. And this equals ma. So, the acceleration is just t cosine 30 over m, if we were doing this numerically. Okay. So that's tension. I'm sorry, that's all it is. Let me try to make it more exciting.